Snails. It's a good introduction, isn't it, when you watch it? Have you got your books open, ready to go?
Yeah.
All day, every day.
I hate when you step on a snail and it makes that noise.
Poor snail. Don't step on a snail.
Caterpillar. And then don't tell them to be crunch. And then you crunch it and then your foot just stays and like half it.
This is a great introduction. Right, snail race game. What we're looking for is we're looking to answer the question, which snail will win? Sorry.
Snail game.
Which snail will win? So basically, we've got the snails from 1 to 12. Okay, 1 through 12. Right, and just to remind you, we roll 2 dice and we add the scores, and that's the winning snail for that round. That allows them to move. So just to remind you. So if we have a 2 and a 3, the snail that moves would be
5.
the 5. So what we want to do is we want to work out what is the probability of each snail getting to move each time. And then the one with the highest probability will likely be the one that wins. So we are looking now at what is the theoretical probability. Right? And then we would try and prove that experimentally. So, if I wanted to know then, what is the probability of snail 1 moving? Now, you told me that was 0. Because?
It's not possible.
Because it's not possible. There's 2 dice. Right? It would be possible if there was only 1 dice, but then we'd only have snails up to 6. Right? 1 through 6. Now that doesn't help us really understand our probability, because it's like, what's that out of? Well, 0 out of anything is still 0, so we can just specify 0. So the question is then, well, what would be the probability of allowing 2 to move? What would be the probability of allowing 7 to move, and so on? So we need to look at that. Now, during the game you told me it was something out of 11, because you were looking at the number of possibilities. Pardon? That's kind of the right way of thinking about it. But what has happened is a common thing, which is you've not really considered all possible outcomes. So I want to know how many possible outcomes. Because I think you already know that that is what goes on the bottom of your fraction. So, for instance, if I want to know the probability of 2 moving, I need to know how many ways there are of getting 2 out of the total number of possible outcomes. So let's have a look at how we're going to do that. Now, I'm going to introduce, well, maybe not introduce to you, a sample space diagram. Have you heard of a sample space diagram?
No. It's not like a Venn diagram.
It could be, actually. Venn diagrams are going to come into probability. In this case, it's not. A sample space diagram is not a Venn diagram. What it is I'm going to list, let me know, by the way, if you need to write this down.
2 and 3, 3, and then 2 and 4, and then 2 and 5,
1, 2,
etc. And then you do 3 and 4.
Yeah, so we could try and list all the possible outcomes.
There's 12 sides. That's just like 12.
Well,
It's not
this is the thing we need to discuss.
Yeah, but if you're looking.
So I'm going to draw a sample space diagram, because I don't want to anymore just list them randomly as a table.
36 alpha.
Okay, so suddenly your outcomes have changed. We have got to add the 2 dice scores. So we could have a 1, a 2, a 3, a 4, a 5, or a 6 on 1 dice. We could have a 1, a 2, a 3, a 4, a 5, a 6 on the second dice. Okay? And when we add those together, we get the score that moves the snail. So if I want to know, for instance, how many 2s am I going to get? Well, yes, you work out the number of ways of getting 2. So 1 add 1 will give me a 2. Is there any other way of getting a 2?
No.
No. So if I go back up to my probability of getting a 2, I know there is only one way of getting a 2. But what are the total number of outcomes that I could get?
36.
36.
Confused.
Oh, 6 times 6.
How many outcomes are there? Now this is what confuses people to start with. What you consider, or sorry, what you don't consider is that some outcomes occur more than once, but they must be considered separately. Okay? So for instance, let's have a look at how many ways of getting a 7.
0.
Well, I know that 1 and 6 gives me a 7. I know 2 and 5 gives me 7. I know 3 and 4 gives me 7. I know 4 and 3 gives me 7. 5.
So that's going to be, there's going to be 2 3s, 3 4s.
That's very
5
satisfying.
6.
Looks like little birds. 7, 7, 7. Little birds.
Right, now this is the thing. What you tend to do, and I heard you do it, you were going through the combinations. You went 2 and 5, 1 and 6, 3 and 4. That makes 7. So 3. But they happen, you've got to consider
Opposite way.
the dice the other way around as well. So we actually have 6 ways of getting a 7. Right? So my probability is 6 out of 36. So now you can see that getting a 7 is 6 times as likely as getting a 2. Alright? So we can fill this table in, and then we would know the probability of them all. So for instance, how would I know the probability of getting, well, let's see, the ones you said were close are 6, 7, 8. So what's the probability of getting a 6? It's going to be nice, it's just going to be there. So what's the probability of getting a 6?
5 out of 6.
5 out of 6.
What are you going to do?
So an 8's also going to be 5 over 36. 8 is also going to be 5 over 6.
So how do I get an 8? 6 and 2.
8's on.
5 and 3.
3 and 5. 5 and 3. 4 and 4 is also.
5 out of 36.
So actually, the probability of getting a 6 and getting an 8 are equal, but slightly less than getting a 7. Hence why, in the race,
7 keeps winning.
7 keeps winning, but it is a close race between 6 and 8 and 7 as well. What's the probability of getting 5?
4 and 1.
4
2
and 3.
3 and 2.
Okay. So 5, 1, which you thought, well, that's a bit of a blip. Well, actually, the probability of 5 is still 4 out of 36, which is not that far off, is it? From getting 6, it should be less. But again, if we ran that game more often, 5 wouldn't win as many times. Right? What's equal in probability to getting a 5?
9.
Getting a 9. So we've got 6 and 3 and so on. Okay. And we can fill out our table. So we've got, 4, 4, 4, and we've got 10, 10, 10. 3 out of 36. Okay. We've got 3, 3. We've got 11, 11. And then the final one that we've got is 12. So the probability of getting a 12 is 1 out of 36. So the common mistake is to say that everything has a 1 out of 11 chance because there's 1, 2, 1, 3, 1, 4 and there are 11 numbers. But it's not to do with that, it's to do with how many possible ways are there of getting it, and you must consider things that you think are another way round. Okay. So, sample space diagram, probabilities, probability notation. So we've got the probability of getting a 10 to win would be 3 out of 36. Right, what I would like to do though is at this stage, let's consider all the possible things that that 3 out of 36 means. And we would use this word here.
Expectation.
So I would expect to happen. So probability is all about what you expect to happen. So expectations. So what does 3 out of 36 mean? Well, 3 at the moment is the number of ways of getting 10. And 36 is the total number of outcomes. Now another way of saying number of ways of getting 10 would be number of successes. So you might hear it say in success, right? Out of the total number of outcomes. Right, but what does it mean as well? 3 out of 36. Anyone want to interpret that for us? Right, okay, simplification. We can simplify to. What does 3 out of 36 simplify to? 1 out of 12. Okay. Now, just to say to you, in probability, you normally don't have to simplify your fractions. Because when we move on to combined probabilities and things, you don't want to have simplified fractions. You want it all, the big denominator, you want to be able to add them all together. If you start simplifying, they won't all simplify to the same denominator, and you'll have to go back to the full denominator that you started with. So,
sounds stressful.
In your exams, you will not normally be asked to simplify the probabilities. So you can just state the probability as a fraction and move on. Right? Okay. For this word expectation, what does 3 out of 36 or even 1 out of 12 mean to you?
36 times you're going to get that.
Okay, so we've got not likely, but that's a bit kind of simplistic at this stage. I would like, in using the word expectation, so maybe I could start you with, I would expect.
I like math because there's no words in it.
Let me start you off. I would expect
Out of 36.
1 10 every 12 goes.
Why you said 110? Oh, because it's 10.
I wrote 1 10 as in there are 1
A single
10. Yeah?
Right.
One lot of 10. Alright?
And Missy got water.
So that means, this is the thing. So for instance, I could say to you, if I rolled those dice 48 times, how many 10s would I expect to get?
What times
Oh, they
what
repeat
makes
that? How many
12
times
times what
did you
makes
do
48?
48?
So if I would roll the dice
So
48 times, I would expect 10 to win 4 times.
Right.
On a bigger scale, this probability also would say, if I were to do the race game 48 times, how many times would 10 win overall?
0, 3, 1.
4.
Really?
Same thing. The probability of 10 winning is the same whether it's winning each round or winning overall. Yeah? But 4 out of 48 is not very big, no? So it's not likely to happen very often. It's very unlikely. It's not likely to happen. But it has a theoretical probability of 4 out of 48. So this is something else to get your head around. That 4 out of 48 is not just each round, it's the whole game as well. So I would expect 10 to win once every 12 goes. Does that make sense?
We should test it on
Yeah, we should test it out.
Once
every 30.
At 48 goes. Now that's theory. Will it happen?
No. It
No.
could.
So if I only do my game 48 times, 10 could win 4 times. I'd be very lucky for that to happen, right?
But
I
no,
could at
because
least win
7 has
once.
a lot more.
Because life don't work like that.
Well, the thing is,
Yeah.
it could happen. It's not. You can't say it won't happen because it's not very likely. It could happen.
But there's so many
It could
other
happen more.
numbers.
How again would I get it more realistic? Like, so I might not get 4 out of 48, but I might get 8 out of 96. Because if I double it, yeah? If I were to do it 1,000,000 times, I would probably get very, very close to 10 winning 4 out of every 12 times if I did it 1,000,000 times. If I only do it 12 times, it's probably not going to end up at being 4. It might be, but you know, there's a very good chance. Now that's the difference between theoretical and experimental. Okay, so then that takes me back to, all right, if I were to change this game, okay, if I were to change this game to you multiply the scores.
Oh, that's a different. You got a different outcome.
Would it change this? So first of all, let's talk about changing. So I'm going to do snail race, right? But instead of adding, we're not going to add anymore. We're going to multiply the scores. Okay, multiply the dice. So, for instance, what are my snails going to be labelled as? 1,
2,
2,
3,
4.
It should be 6.
5, 6, but then
7, 8, 9.
No, it'd be 14, 28.
so what's the best way of doing this?
Nothing.
Sample space diagram again, though.
Yeah.
So
Is there a good way to do it?
to figure out what are my things. So I could get a 1, a 2, 3, a 4, 5, 6. I could get a 1, 2, 3, 4, 5, 6. So what are my outcomes? I could get 1, 2, 3, 4, 5, 6.
2,
Yeah.
4, 6, 8, 10, 12.
So I can do 1,
3, 4,
6. I can get 4, 6, 8, 10, 12. This would be
9,
12, 13, 18, 16, 20, 24,
25,
28, 32, 28.
36.
okay.
Oh,
So why didn't we do the snail race game using multiplying? Because how many snails would I have had to have had? 1, 2, 3, 4, 5, 6. Would I have had
36.
7? No. Alright. So, what? Maybe we're not going to do a snail race game because we've got too many. But let's still ask the questions then. If I take 2 dice and I multiply the results together, I'd like you to do this now without just do it in your book. What would be the probability of me ending up with a prime number answer? What would be the probability of me ending up with a square number answer? What would be the probability of getting an even number answer? What would be the probability of getting a multiple of 4? Okay, well, however you want to do that in your book, I would just like you to have a go at answering those questions. So you may need to do the table, yes, in your notes.
Times to get.
Whoa, can you like copy me?
Right, I know you're still doing it, so I don't want to interrupt too much. What is every single one? What's the denominator?
36.
It's always 36 in this case. So you've just got to figure out, that's the total number of outcomes, you've got to figure out how many are what I'm looking for. So let's just check. Do you know what the prime numbers are? So we've got 2, 2, 3, 3, 5, 5.
You said 7.
7 is a prime number, but it's not up there. Is there anything else that's up there?
Nope.
No. Because just by the fact you're doing something times something, you're not going to get a prime number. So the probability of getting a prime number is
6 out of 36.
6 out of 36.
Well, I got 5 out of 36. I didn't count the other 5.
The common mistake would be to include 1 as well. Okay. Right. So square numbers. What are the square numbers?
1, 4, 9, 16, 4, 9, 36.
Okay.
So
So we got 1. Everyone, stop. 1, 4, 9, 16, 25, 36. 4 also. Is that there and there?
I put.
Yeah.
It's 8.
Is that it?
Yeah.
4, 5, 6, 7, 8.
Because 4 is the only square number in the 1 to 6, apart from 1. Therefore, it's the only one that 1 times it gives them. So we actually end up with
8.
8. 8 out of 36. Okay? 8 out of 36. What about even numbers then?
27.
27. I got
27.
I got 26.
So we got 1, 2, 3, 4, 5, 6, 7,
8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27.
Oh, I got 26.
so 27 out of 36. Okay, and then finally, yeah, I did, they just don't show up. Right, what about the multiples of 4 then? So that would be 4,
8,
8,
12, 16,
4.
20, 24,
2.
12, 16, 20. So we've definitely got those ones.
There's another 12.
There's another 12,
And another 12.
and another 12, and 36.
15.
I got 14.
Anything else?
8 is not 15. That's like 14. 14. 15.
I missed that 12.
14, 40.
14. Yeah, 14. There's 15.
1, 2,
Oh, you're counting.
16.
Yeah. So we've got 1, 2, 3, 1, 2,
Because it's 6 going down to
6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
What?
Don't count the 16 twice.
Oh, then it isn't.
You counted 16 twice.
No, I had 14.
Oh, okay, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Alright.
Okay.
I'm happy now. That's it.
Right.
I'm getting used to it.
I'm going to introduce you to some very important vocabulary now.
Oh, okay.
Right. What's the probability of getting at least 7?
At least 7. At least 7 what?
0. 0.
It's at least.
It's 0
Right, so,
at least.
no, right, listen. So this is the word, isn't it? I'm glad I went through it. What does those words at
Anything above
least?
7.
So it actually is 7
And more.
and above. Okay? So you've got to include 7, at least 7. So if I said to you, and you would understand this, if I said to pass your test you need to get at least 50%, you would know that 50% or above would pass. Yeah? So,
22.
what if I did this? What if I said to you, and this is important as well, excuse me. If I introduce this, so the probability of at least 7 is found by doing 1 minus the probability of less than 7. Now this is an important part of probability as well, because the probability of everything has to equal 1.
36.
So is there anything left out if I consider 7 or more and less than 7? Is there anything else? Or does that include everything? That includes everything. So you've got to be careful when you look at this vocabulary. So at least 7 means 7 or more. Less than 7 is everything else. Now, sometimes it'll be easier to work out the other side of it. So that at least 7, I could say, well, why don't I actually count the less than 7s? Okay? So the less than 7s, as I know there's less of them.
You missed 4. Like 4 of them.
5. Come on, pen work. 6. Alright, so I've got 6, 7, 8, 9, 10, 11, 12, 13, 14. So I can consider it like this. I can do 1 minus 14 out of 36 will give me what I want. Because it all has to add up to 1.
So 16.
Now, the 1 bit, the 1 is considered when I consider everything. So in this case, I could actually consider, instead of 1,
36.
I'm going to consider, well, I consider everything. So 36 out of 36, which is the 1.
Oh, so then it's
If I subtract 14 out of 30, I get...
Oh, you got 22 out of 36.
Yeah, we connected the dots. We're the dots. Slowly.
Okay? Now I should be able to confirm that by looking at there and going, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay? You get it? Make sense? Okay. So this is, you will see this in your textbook, the 1 minus the probability. Okay? So I'm just going to, I need to summarise that for you and say the probability of an event happening is equal to 1 minus the probability of that event not happening.
Oh.
Does that make sense?
Yeah.
So that's like the fundamental theorem of probability. It must add up to 1. Another way of saying it is if I add the 2 together, I get 1. Or 100% or a fraction where it's all that. But you will see this, they'll sometimes refer to it in an exam question or anything like that. Okay. So, anyone still writing? Don't want to move yet. So, for instance, if we look back at the list that we were just doing before, the evens, the multiples of 4s and that kind of thing, what would be the other side to that event? Do you know what I mean? Can I move yet?
Yep.
So, what I mean is, what would be the opposite to finding the probability of prime? Go on. Loud and proud. Not prime, yeah? the probability of it not being prime.
Oh, just ring some bells.
Wait, what?
Like 2.
So the probability of not prime would be
36.
1 minus
1 minus 6 over 36, which would be
So smart.
30 out of 36.
That's what I said.
What would be, do you know what not prime are sometimes called?
Unprime.
Integer.
No, I'm pretty sure composite numbers.
Composite numbers.
Where
They've
have
got-
we done this? I literally in math class like a year ago.
I know I've done it with year 7s and year 9s, primes and composites.
Miss Harrison.
You've probably done it before.
Harrison.
Right, what's the probability, what's the opposite of
Not square.
not square? Yeah?
1 minus square.
1 minus square. What's the opposite to?
Odd.
Good, I thought you were going to say.
I was gonna say
Not
that.
Yeah, the probability of odd would be,
But what's the opposite of multiple?
which is,
Not even.
but
Not
what's the probability?
Minus
9.
36
No, it's
9 out of 36, yeah?
no, it's not.
What would you say the opposite to multiple of 4 would be?
not multiple.
Not a multiple of 4. And we've already done the opposite of at least 7 would be,
Ow.
We just did this.
we've just
Seven and above.
Less than 7.
less than 7.
Oh, sorry, I was
The
doing
opposite.
I'll try to
When Taylor's word.
Okay,
more than 7.
It's not that.
right, I've got something. Cut, quiet. I've got something for you to work out for me.
Okay.
Alright? Got another game. Okay? Well, no, I'm not actually going to play the game. I roll a die.
A dot.
I roll up.
Right?
It's not fair.
This die has the numbers on it 0, 1, 1, 2, 2, and 3.
Pigeon, this is pigeon obviously on you.
Not quite, no.
No, it's not to be.
I roll it twice.
Where's my shoe?
Okay?
Me and
One's confused.
Big Mo?
I add the scores.
Oh,
That's the
can we
scores.
make a diagram?
Okay? I add the scores.
Right.
I win if my total, okay,
It's 3.
is prime.
Do you guys remember
So that's
Brady
2,
Pig?
3, 5.
So what is the probability of a win? Over to you. You work it
One
out.
As a
minus
class,
not
as a table, as a person. 4, 5, 6, 7, 8, 9.
Just to finish off very quickly then. So we've got our grids. Everyone, we're going to add the scores. So we've got 0, 1, 1, 2, 2, 3. Same thing.
Zeros.
Yeah, I need to add that one.
Okay. We've got 2, 2, 3, 3, 4, and so on. Right?
I didn't count.
If we count, everyone stop packing up for a moment. I'm in control.
Yep.
Should be. So the probability of winning, we know will be out of 36. How many primes were there? Do we agree?
22.
22. Let me count that again.
22?
4, 5.
We agree there are
I agree.
22 prime numbers.
19.
I forgot to count. I don't know.
You don't have to.
You forgot to count 2.
I was just 2 zeros.
Okay, that is
Right.
Oh, I forgot about 0.
I didn't count 0.
22. It's 0?
No, 0 is not a prime number.
No, I mean like I didn't make the line for 0. I asked.
Yeah, me neither.